I'm Peter Zoller, and I'm a professor for theoretical physics at the University of Innsbruck and scientific director at the Institute for Quantum Optics and Quantum Information. And my field that I'm working in has been now for a very long time atomic physics, quantum optics at this interface with quantum information and quantum simulation in particular. I should maybe say at the very beginning that I think that quantum simulation is one of the most promising applications that we have in this quantum information context. What we do there is this, that we are solving many body problems on quantum machines, with applications from condensed matter problems to many body problems that we might be interested in quantum chemistry to high energy physics and so on. And our ongoing work in the context of PASQuanS at the moment is that we are developing algorithms for high energy physics that we can hopefully run on hardware that's becoming available in the consortium that we have over here. On the other hand, we are also very interested in, for example, quantum verification, where you give us a quantum machine and we are trying to find out what the underlying Hamiltonians or Liouvilleans are that govern the time evolution of the system. So it's a way of characterizing and therefore then also verifying that quantum simulators operate correctly, in particular in the regime where we cannot test them classically, but they are then sort of in the regime where we cannot compare with any classical computations. I would say that the most rewarding aspect of our work has definitely been that we as theorists develop ideas and concepts like how to build a quantum computer and also how to build a quantum simulator, and ideas that we came up with now, 25 years ago, they are now realities in the lab. And this is super rewarding, to see that what used to be somehow scribblings on some blackboard, are now reality in the lab, and they are the ones that are the platforms that are being pursued in a consortium like this one here, where definitely I would say Europe is one of the leading places worldwide in this context. Yeah, so as I said before, I think that Europe is very strong. We have many of the leading groups that come in the context of quantum simulations are from Europe. And to bring them together in a consortium like what we have here, I think is something very important, something also very fundamental. And this ability to collaborate together at a very high level and have meetings like the one that we're having here right now, I would say that this is part of the strength, but it's also part of the fun of being a member of this community here, where a lot of things are going on. And this collaboration, I think, is very fundamental to scientific progress in Europe, to connect it to quantum technology, but also to have colleagues that work on very similar things to move things forward. And collaboration is always the effective way of moving things forward. Well, again, I would say that quantum simulation that we talk about over here is probably one of the prime answers, be it in condensed matter physics or high energy physics, quantum chemistry or whatever. And but I would also say that there's some other topics. I'm personally very much fond of a situation where we do, for example, quantum metrology. Quantum metrology, we build quantum sensors. And we want entanglement in these quantum sensors to get then higher precision, in what we measure. And in order to engineer the corresponding entanglement, quantum simulators is sort of one platform of doing this. And so out of a programmable quantum simulator then becomes a programmable quantum sensor, where we can run algorithms that are basically measurement protocols that where the quantum machine provides the entanglement, that allows us to measure with higher precision, but at the same time also the entanglement capabilities in the laboratory. And at the same time, this quantum simulator not only produces an interesting quantum states, but they are useful per se. So for me, that's an example of an relevant quantum advantage, where a machine produces interesting entanglement, has these capabilities, but then it is the same machine which then uses then, for example, in the context of some quantum metrological protocol, to use this to get then a higher precision in measurement. And quantum advantage, reaching quantum advantage is one of the main goals that we have here. And that's, I think, what we can achieve this way.